Hello and welcome to all students. In this lecture, we learn about a differentiation and we study the subtitle Gradient of Scalar Valued Function and problems based on gradient of scalar valued function. Okay. So let us see examples on algebra of gradient. Algebra of gradient of scalar valued function. In the last lecture we studied about the algebra of scalar valued function. Now here consider the question number 1. Let f of x comma y is equal to 3x square plus 9x into y and g of x comma y is equal to 4y square plus 7x. 4y square plus 7x. Now find, here we have to find gradient of f. After that we have to find gradient of g, then gradient of f plus g, then gradient of f minus g, gradient of f into g, and then gradient of f upon g at point 1 comma minus 1. So while finding all these gradients, so if we find the gradient of f and gradient of g, then the remaining gradients can be found by using the algebra of gradient. So keeping in mind these two functions, f of x comma y is equal to 3x square plus 9xy and g of x comma y is equal to 4y square plus 7x. So we write the answer. Given that f of x comma y is equal to 3x square plus 9 times xy and g is a function g of x comma y is equal to 4y square plus 7x. Let a is equal to 1 comma minus 1. That is the given point. Here we will find partial derivative of f with respect to x, and it is equal to 6x plus 9y, and partial derivative of f with respect to y is 9x. आता पार्शियल डेरिव्हेटिव्ह कशी फाइंड आउट करायची हे तुम्हाला माहिती आहेच. तर बघा f इज अ फंक्शन. f फंक्शन काय आहे तर 3x स्क्वेअर प्लस 9xy बरोबर, आणि फंक्शन f चा पार्शियल डेरिव्हेटिव्ह विथ रिस्पेक्ट टू x, सो डो f बाय डो x इज इक्वल टू, so partial derivative of first term with respect to x is 6x and partial derivative of second term of f with respect to x is 9y. Okay, so at that time we have to keep, while finding a partial derivative with respect to x, we have to keep variable y constant. Therefore 9y is constant and the partial derivative of 9x into y is 9y. So similarly we find the partial derivative of f with respect to y, and here the variable x we have to keep constant. So first term 9y square is a constant and its derivative is 0, and the second term is 7x and its partial derivative with respect to y 7x and its partial derivative with respect to y. Okay, dou f by dou y, dou f by dou y. Okay, partial derivative of f with respect to y is 9x, it is correct. Okay, 9x. Now also we find the partial derivative of g with respect to x, and it is 7, and partial derivative of g with respect to y, it is 8y. Okay, now we will find the values of all these partial derivatives and functions at point a. So what is the value of f at a? It is f of a is equal to f of a is 1 comma minus 1, and it is equal to 3 into 1 square plus 9 into 1 into minus 1 is equal to 3. So 3 into 1 square is 3 minus 9, and 3 minus 9 is minus 6. 3 minus 9 is a minus 6. So now we find the uh, value of g at point a, and it is equal to g of 1 comma minus 1. It is equal to, as g of x comma y, that function is defined like this: 4y square plus 7x. So on the same line we will write the value of g of 1 comma minus 1, and it is equal to 4 into minus 1 square plus 7 into 1 plus so it is equal to 4 into 4 plus 7 is equal to 11. Dou f by dou x at point a is equal to dou f by dou x at point 1 comma minus 1, but that partial derivative has is a function 6x plus 9y. So 6 into 1 plus 9 into minus 1, so 6 in minus 9 is minus 3. After that we find a partial derivative of f with respect to y at point a, and that function is 9x. So 9 into x is 1, so 9 into 1 is equal to 9. So after that find the values of partial derivative of g with respect to x at point a, and that function is 7. So partial derivative of g with respect to x at point 1 comma minus 1 is a constant number 7. Partial derivative of g with respect to y at point a, finally in the final line. So partial derivative of partial derivative of g with respect to y at point a is equal to dou g by dou y at point 1 comma minus 1, and that function is 8y. So 8 into y is minus 1, so 8 into minus 1 is equal to minus 8. So in this way we will find all the values at point a. Now let us find the gradient of f at point a. Gradient of f at point a is equal to, so by definition the gradient of f is nothing but a vector with two components. First component is dou f by dou x at point a, and the second component is dou f by dou y at point a. So dou f by dou x at point a has value minus 3, and dou f by dou y at point a has value 9. Therefore gradient of f at point a is equal to minus 3 comma 9, vector minus 3 comma 9. Now we will find gradient of g at a is equal to dou g by dou x at point a comma dou g by dou y at point a. So it is also gradient of g at a is also a vector with two components. The value of first component, partial derivative of g with respect to x at point a, is 7, and the value of the second component, partial derivative of g with respect to y at point a, is minus 8. So gradient of g at a is a vector 7 comma minus 8. Now we find the next identity, gradient of f plus g at point a. Gradient of f plus g at point a is equal to by the identity gradient of addition of two functions is equal to addition of their gradients. Therefore, gradient of f plus g at point A is equal to gradient of f of A plus gradient of g of A, or it is equal to, so gradient of f at A is a minus 3 comma 9 vector plus gradient of g at A is 7 comma minus 8. So we know that how to add these two vectors. So add first component into first component and second component into second component. So we get again a vector minus 3 plus 7 comma 9 plus minus 8, and it is equal to 4 comma 1. Now we find the gradient of f minus g. So again we use the algebra of gradient. So gradient of subtraction of two functions is equal to subtraction of their gradients. That thing is known to us. Okay, therefore gradient of f minus g at point A is equal to gradient of f of A minus gradient of g of A. So in the second step, it is equal to minus 3 comma 9 minus vector 7 comma minus 8. So we know that how to take a subtraction of two vectors. So subtraction of two vectors is again a vector with two components. So first component is minus 7 minus 3 minus 7 comma second component is 9 minus minus 8. So minus 3 minus 7 is minus 10, and 9 minus minus 8 is 9 plus 8, and it is 17. Thus the gradient of f minus g at point A is a vector minus 10 comma 17. Gradient of f into g at point A is equal to, now again we use here the identity, or we can say that algebra of gradient of two functions. So gradient of product of two functions. So gradient of f into g at point A is equal to f of A into gradient of g of A plus g of A into gradient of f of A. But we have calculated the value of f of A, it is minus 6, and gradient of g at A is a vector 7 comma minus 8, plus gradient of value of g of A is 11, and the value of gradient of f at A is a vector minus 3 comma 9. Now just multiply by the scalar to the vectors, we get a next step, third step. It is a vector addition of two vectors, minus 42 comma 48 plus minus 33 comma 99. So addition of these two vectors is minus 75 comma 147. Thus the gradient of product of functions f and g at point A is a vector minus 75 comma 147. Now gradient of f upon g at point A. Gradient of f upon g, or f by g at point A is equal to, we know the formula, or we know this identity, and it is equal to g at A into gradient of f of A minus f of A into gradient of g of A divided by g of A square. So we put the values of all these gradients and the values of these functions in this quotient. So it is equal to 11 into vector minus 3 comma 9 minus minus 6 into vector 7 comma minus 8 whole divided by 11 square. It is equal to minus 33 comma 99 plus 42 comma minus 48 whole divided by 121. So in the numerator, the addition of these two vectors is 9 comma 51, and divided by 121. So divide by these 121 to each component. So 9 divided by 121 comma 51 divided by 121. Thus the gradient of quotient of these two functions is 9 upon 121 comma 51 upon 121, vector with two components. Now we see the relation between the total derivative and gradient. So this is actually a theorem. Let S be the non-empty subset. Let capital S be the non-empty open subset of Rn, and if f from S to R is a differentiable at A belongs to S, then gradient of f at A exists, and the total derivative of f at A is given by derivative of f at point A in the direction of h is equal to gradient of f at A dot product with vector h. So this is very important relation between the total derivative and gradient. So we use this relation while solving the problems. Now consider the relation between the directional derivatives and the gradient. Let capital S be the non-empty open subset of Rn, and if f from S to R is differentiable at A belongs to S, then for any vector u belongs to Rn, the directional derivative of f at point A in the direction of u is given by. So the directional derivative of f at point A in the direction of u is nothing but the gradient of function f at point A dot product with vector u. So this is also a very important relation. So based on this relation we will solve the problems in the next slide. So consider the example. Question number 1. Question number 1. Find the total derivative of the following function using gradient of f. So once again, find the total derivative of the following function using gradient of f. So f of x comma y is equal to 3x square y plus 7y into sin x plus e raised to the power xy at point 1 comma 1. So we have to find the total derivative of this function at point 1 comma 1. So function is 3x square y 3x cube y plus 7y into sin x plus e raised to the power xy. So we will find the total derivative. So for that, okay, write the solution. Given function is f of x comma y, it is equal to 3x square, given function is f of x comma y is equal to 3x cube y plus 7y into sin x plus e raised to the power xy, and point is a is equal to 1 comma 1. Here we use following relation to find total derivative of given function. The relation is total derivative of f at point A is equal to gradient of f at point A dot product with h. Here partial derivative of f with respect to x is equal to 9x square. So we know that how to find partial derivative of function f with respect to x. So while finding this derivative, we keep the other variable, say other variable means y constant, and we find the normal derivative. So partial derivative of f with respect to x is equal to 9x square plus 7y into cos x plus y into e raised to the power xy, and dou f by dou y is equal to partial derivative of f with respect to y is 3x cube plus 7 into sin x plus x into e raised to the power xy. So these two are the partial derivatives of given function f. Now gradient of f of x comma y. Gradient of f of x comma y is nothing but a vector with two components, and that vector is dou f by dou x comma dou f by dou y. So gradient of f at x comma y is equal to first partial derivative is 9x square, or first component is 9x square plus 7y into cos x plus y into e raised to the power xy, comma second component is 3x cube plus 7 sin x plus x into e raised to the power xy, and gradient of f at point 1 comma 1 is equal to, so in the above formula wherever is x and y, put the values of x and y equal to 1. Okay, so after putting the values of x and y equal to 1, we have gradient of f at point 1 comma 1 is equal to 9 plus 7 into cos 1 plus e, comma second component is save 3 plus 7 into sin 1 plus e. Thus the total derivative of f at point 1 comma 1 in the direction of vector u is equal to, gradient of f at point 1 comma 1 dot product with vector u. So gradient of f at point 1 comma 1, it is calculated above, and we take a dot product with vector u, and vector u is u1 comma u2. So if I take a dot product, you will get a scalar quantity. So total derivative is nothing but a scalar quantity u1 into bracket 9 plus 7 times cos 1 plus e plus u2 into 3 plus 7 times sin 1 plus e. So in this way we find the total derivative of given function at point 1 comma 1 by using the relation between total derivative and the gradient of a function f. Let us take example number 2. Find the directional derivative of f of x comma y comma z equal to x square plus 2y square plus 3z square at point 1 comma 1 comma 0 in the direction of vector I minus j plus 2k. Now we solve this problem. Given function is f of x comma y comma z is equal to x square plus 2y square plus 3z square. Given point is a equal to 1 comma 1 comma 0, and vector is u equal to I minus j plus 2k is equal to 1 comma minus 1 comma 2. We find the directional derivative of function f using the following relation. Du f of a is equal to gradient of f of a dot product with vector u, or once again the directional derivative of f at point in the direction of vector u is equal to gradient of f at a dot product with vector u. Here gradient of here partial derivative of f with respect to x is equal to 2x, and partial derivative of f with respect to x at point a is equal to dou f by dou x at point 1 comma 1 comma 0. It is equal to 2 into 1 is equal to 2. Again partial derivative of f with respect to y is equal to 4y. it is equal to dou f by dou y at point A is equal to dou f by dou y at point 1 comma 1 comma 0 is equal to 2 into 2 is equal to 4. Now finally find partial derivative of f with respect to z is equal to 6 z, and this implies dou f by dou z at point A is equal to dou f by dou z at point 1 comma 1 comma 0. It is equal to 6 into 0, it is equal to 0. Now we find the gradient of f at point A. It is equal to dou f by dou x at point A, dou f by dou y at point A, dou f by dou z at point A, and that factor is 2 comma 4 comma 0. Now we find the directional derivative of function f at point A in the direction of vector u, and it is equal to gradient of f at point A dot product with vector u. So gradient of f at point A is 2 comma 4 comma 2 comma 4 comma 0 dot product with 1 comma minus 1 comma 2. It is equal to 2 into 1 plus 4 into minus 1 plus 0 into 2. It is equal to 2 into 2 minus 4 plus 0. It is equal to minus 2. Thus the directional derivative of function f at point A in the direction of u is equal to minus 2. Suppose, okay, so thus now we have a question number 3. Okay, so question number 3 says that suppose f of x comma y, if differentiable at A belongs to S, which is subset of R2, and if the total derivative of f at point A along the vector 1 comma 2 is equal to minus 5, and total derivative of f at point A along the vector minus 1 comma 4 is equal to 6, then find partial derivative of f with respect to x at point A and partial derivative of f with respect to y at point A. So problem is very simple, and how to solve we will see here. Solution is given that the derivative of f, total derivative of f at point A along the vector 1 comma 2 is equal to minus 5. Also given that the total derivative of f at point A along the vector minus 1 comma 4 is equal to 6. As we know the relation between total derivative and directional derivative, total derivative and gradient of function f. So we have total derivative of f at point A along vector u is equal to gradient of f at A dot product with vector u. So again we write derivative of f at point A along the vector 1 comma 2 is equal to gradient of f at point A dot product with 1 comma 2. But that total derivative left hand side is given to be minus 5, and it is equal to gradient of f at point A dot product with 1 comma 2. But gradient of f at point A is nothing but a vector fx at A comma fy at A dot product with 1 comma 2. Now left hand side is as it is minus 5, and it is equal to on the right hand side we take the dot product of these two vectors fx at A plus 2 times fy at A. So this is our one relation or one equation that we will use further. Now we find, again we take the same relation, derivative of f at point A along the vector u is equal to gradient of f at point A dot product with vector u. Here vector u, here total derivative of f means df of A at point minus 1 comma 4 is equal to gradient of f at A dot product with minus 1 comma 4, but left hand side is given to be 6 and gradient of f at a dot product with minus 1 comma 4. So left hand side, in the next step, left hand side is as it is 6, it is equal to vector with two components fx at a comma fy at a dot product with minus 1 comma 4. So 6 is equal to minus fx at a plus 4 into fy at a. Now we have two equations. First equation is minus 5 plus fx at a plus 2 times fy at a, and second equation is 6 is equal to minus times fx at a plus 4 into fy at a. So if we add these two equations, then we will get 1 is equal to 6 times fy at a. So fy at a is equal to 1 upon 6. So put the value of fy at a in any one of these two relations, in these two equations, and then we will find the value of fx at a is equal to minus 16 upon 3. Thus our problem is over. So if you have any problem, you can contact. Okay, and our lecture is over here. Thank you very much.